All right, so summary statistics is what we're playing with. And so far, we've gone over that it's important to know how many numbers or elements are in your data set. Often that's called the sample size. We usually give it the letter N. The mean, which is our average, that's usually given the letter X bar. And a little more detail on that, that's always the sum of the values divided by the count, how many there are. The standard deviation is a bit more complicated. It's a measure of the average spread of the data from the center being the mean, more specifically. So the idea of deviation is distance from the middle. So any one of us, like we have a height. So our height is X. We can figure out our deviation just by taking our height and subtracting the average. If you're above average, you'll get a positive deviation. And if you're below average, you get a negative deviation. The thing about the mean, though, it finds the value that optimizes sharing throughout the whole group. So the deviations even out with the mean. To deal with that, to find the standard deviation, what we do is we square these numbers to get rid of the positive and negative, or to get rid of the negative signs. And then we add them all up. And this is the mathematical symbol for add things up, the capital Greek sigma. After we add them up, we divide by the sample size -1, and then we take the square root. And I have a note in the homework that says never do this by hand. Okay, you can, it's a pain in the butt. We're not going to do it. We're going to push a button on the spreadsheet that calculates the standard deviation instead. But if you really wanted a formula, that would be the formula for the sample standard deviation. Other important numbers. We have the minimum, quartile 1, the median, which could be called quartile 2, quartile 3, and the max. These are what are called the 5-number summary, and they split your data up into 4 quarters based on the sample size. So if your sample size was 80, then from the min to quartile 1 will be about 20 numbers, a quarter of 80. The next 20 numbers in order would be from quartile 1 to the median. The next 20 numbers in a data set of size 80 would be from the median to quartile 3. Does it always come out exactly right? The answer is, nah, it's a little bit wiggly because there's never a number that's perfectly in the right spot. The other thing is, for the quartiles 1 and 3, there is no standard formula for that around the world. So if you use a spreadsheet to calculate it, you'll get one number. If you use another statistical app, you'll get another number. If you look up a by hand method in a book, you get a different number for the quartile. They'll all be in the ballpark of each other, but not necessarily the same number. So just a warning about that. The thing we're doing today that's new is we're going to look at identifying outliers. So sometimes some numbers are way out to the right or way out to the left compared to the rest of the group. How do we decide when something's too far to the right, too big, or too small compared to the rest? So there's a couple of techniques in the book about how to identify when numbers are unusually large or small compared to the majority of data. So to do this, we're going to do some graphics, and let's pick a data set to play with. We've got the About You data for 2023, and that is linked in one of the announcements. And what should we play with today? Since I just mentioned height, why don't we do height? Oops, phone responses. So I am just going to grab the height out of here. I'm going to copy it, and I'm going to make a new spreadsheet to play with it in. I'd recommend you do the same. And it's always a good idea to give your spreadsheet a name. I'm going to call it About You Statistics. And we'll start off by making a histogram. So once you have the data in another spreadsheet, then we're just going to insert a chart. If you need any help getting the spreadsheet or the chart. All right, let's see. What do we got going on here? That's a rather interesting looking chart. Notice I have a huge gap. This is height in inches, and I have some numbers here that are below 10. So it seems people that filled out the data confused feet with inches. So sometimes it's necessary to scrub the data, cleaning up any errors. So to clean this up, I'm going to data, sort range, advanced, say it has a header row, so I keep the title at the top. I'm going to go from smallest to largest. All right, so I'm not going to guess what somebody meant. Maybe they meant to type 50 something. Maybe they meant 5 feet. I don't really know. So I'm just going to delete those from the data set. And then if you do a control down arrow, that should take you to the end of the list. 78 is a reasonable height. So aside from those first few at the top, I think it's okay. So I'm just going to highlight the column again. And I could delete those empty cells. Instead, I'm just going to resort the data. And that'll just pull those up there. All right, so now we got a cleaner data set. And I'm going to insert a chart again. All right, so there's the histogram. So Google, again, just guesses at a starting point based on what it sees as the smallest number. And the largest number decides on how to split up the data. So here it decided on groups of 2. That is on the edge of too many. So I'm just going to go over to customize. Remember, there is no best histogram. I'm going to go for 5. Not bad. Starting at 50. 2 seemed like too many. And I'm just going to stick with 5. That's not too bad. All right, so that's going to be my histogram. I'll make prettier titles later. I'm just going to move that over here. The next thing I want to do is put in the summary statistics. I'm just going to put a title at the top, summary statistics, and go through the statistics I know I need. So for sure, I want to count them, how many there are. I want the mean of the data set, and I like to put the mean and the standard deviation together. I'm going to abbreviate it as STDEV. And then I'm going to skip this one line. Yeah, I'm just going to skip one line there. And then I'm going to do the 5-number summary. The min, quartile 1, Q1, the median, quartile 3, and the max. So it's always a good idea to put labels. So when you look back at the numbers, you know what they are. Count on a spreadsheet is simply count. And since the only thing in there, column A, is the title and the numbers, I can click and highlight the whole column. Spreadsheet says A:(A), which is everything in column A. 229 numbers. I do not want to fill that down. Mean is equals average. And there's a bunch of averages. We want the one that's just average. And since it ignores text, I can highlight the whole column. Standard deviation, STDEV, there's a bunch of options. I recommend the .s version, which is standard deviation of a sample. That's the most common standard deviation calculation. Oops. And then highlights the whole column is fine. Minimum. Now I can see the minimum is 52, but I'm going to use the minimum function to just double check. Highlight the whole column. Quartile. Never use quartile exclusive. It's either quartile or quartile inclusive. I recommend the inclusive one. And here you have to give it the data and which of the 5 quartiles you want. So there's a beginning and end and 3 slices in the middle. So we want quartile number 1. Quartile 0 would be the minimum. Quartile 2 is the median. Use the median function for that. Data. For quartile 3, I have to use the quartile function again. We'll go over another way to do that next week. And again, the quartile function needs the data, and then which of the quartiles I want. I want quartile 3. And then the max, which is also known as quartile equals max, quartile 4. We're just going to use the max function, data, done. Now, I mentioned this before, most spreadsheets suck at drawing box plots. So we're going to just draw our own box plot in here. To do that, what I'm going to do is I'm going to make a copy of the histogram here so I can get the scale down here. And I'm just going to use that scale to draw my box plot, those numbers right there. Print of those numbers. So we have 52, 63.6, 67, 70, and 78. So I'm going to go over here and let's see, copy the chart. Once I've copied it, I'm going to go insert a drawing. And then in the drawing, I'm going to paste it in. Now here, linked means link it to the spreadsheet so that if something changes in the spreadsheet that changes the histogram, that change will be reflected in the drawing. I don't need to worry about that. So I'm just going to paste it unlinked, which is just a picture of it. And I need the scale to draw a decent box plot there. Now, I don't need the whole thing, so I'm just going to crop out what I don't want. So I'm just switching to the crop tool here. I'm just going to bring that down. So really all I want to be able to see is the number line. And after you crop something, you just hit enter or click off of it. So I'm going to use this to draw my box plot. So I'm going to use the line tool now to draw that. And I just want a straight line. So let's see, I'm going to draw the box first. So the box starts at Q1, which is 63.6. So there's 60, there's 65. Right in the middle would be 62.5. So 63.6 is going to be around here-ish. So I'm just going to draw a line coming straight down from there. Something like that. Once you draw a line, then you can go in and do things like change the line's color. So maybe I feel like making a purple line today, and I want it to be a little fatter. That's nice. Okay. And once I have that set, my other lines will look like that. So that's Q1. Q3 is 70. Well, that's easy right here. Just going to draw a line coming down there. And then that's the box for the box and whisker plot. And then in the middle of that, we draw 67, the median. So let's see, 65, 70, right in between is 67.5. So 67's around here-ish, to the best of my ability. So the box has Q1 on the left, Q3 on the right, and the median. Now my median's pretty close to the middle of the box, but it could be way to the left, it could be way to the right. It's just wherever it lands on the number line. Next, we draw whiskers out to the min and the max. So from the edge of the box here, I want to draw a whisker out to where I think 52 is. So let's see, right in between 50 and 55 is 52.5. So a little further back is about 52. So maybe right there. And my max was 78. So 75, 80, 78 is probably around here-ish. So to the best of my artistic ability, there is my box and whisker plot. And sometimes people put little dots or tabs at the end. Sometimes they don't. I'm just going to leave it like that. Cool. Now, I don't necessarily need that scale there, but it might be nice to line it up when I bring it back in. So I'm going to leave the scale there and just do a save and close on this. And it came in bigger than what I copied. So now I have to resize it to match because we want these to line up. So I'm just going to line up the left edge and zoom out. And then grab a corner and rescale it so it's the right size again. There we go. Okay, so there's my box and whisker plot along with the histogram. Now, the relationship between these again, I'm just going to take this into my notebook to draw on it to just illustrate what we're showing here. Screenshot. New page, please. All right, so what does a box and whisker plot do? So again, this mark right here is the min. This mark here is Q1. This is my median in the middle. This is Q3, and this over here is my max. Q1 is the position in the numbers so that 25% of the data is at or below Q1. So approximately 25% of my numbers lives in the stretch from 52 up to 63.6. 25% of the numbers live in that range of values. The next 25% of data values, basically people that took this survey, live in this narrower range right there. The next 25%, the next quarter, live in this region. So again, the difference between a quarter and a quartile, a quarter is in this case a group of people, 25% of the people that took this survey. A quartile is a position in that range of numbers that says stop here to identify that first group of 25%. So a quarter is a group, a quartile is the end of a group, a specific number. And the median is the second quartile. And then finally, the last quarter is from Q3 to the max, and then that's about 25% of the numbers live in that range right there. What should happen is anytime you have a narrow range and 25% of your numbers live there, that's going to correspond to tall stacks in your histogram because they're kind of crammed in. So these are like people living in a city, and over here is people living out in the country. They have more room to spread out. So there's going to be shorter stacks for that group of people. So this is helping me figure out how are the heights of people distributed. And what we find are most heights, people that take my math classes are somewhere between about 64 inches in height and 67 inches in height. What do I mean by most? Well, 50% of my students are between 64 inches and 67 inches. So that's like an observation I could make here. The middle 50% of student heights are between 64 and 67 inches. What other comments can I make? Well, the upper 25% of students have a height from 67 to 78. Was the maximum in this data set. So it just gives me, again, there's a big list of numbers here. Nobody wants to look at that big list of numbers. What they want me to do is summarize it for them. How can I summarize it? Turns out there's lots of ways to summarize it. Right? Just based on the statistics, I can say the average height is about 66.5 inches. Blow this back up again. How should I round this data? The usual rounding rule in statistics is take the calculations to one more decimal place than the data. And I think my data is all whole numbers. Is that true? Oh, somebody entered a 63.6. Interesting. Okay. Oh, 65.5. Did anyone go more than one decimal place? 0.6 again. Looks like we have at most 1 decimal place. Okay. So then I should round these to 2 decimal places. So it's usually the mean and the standard deviation that will need rounding. Sometimes the median will need rounding because the median is not necessarily in the data. Depends on whether it's an even or an odd data set. Q1 and Q3 will often be decimals and sometimes need rounding also. It depends on the data. So in this case, I only need to round 2 numbers. Let's see. Next, what we want to do is check to see, are there any people in this data that are unusually tall compared to the rest or unusually short compared to the rest? And there's a couple of ways to do that. So I want to do that by using first the standard deviation, and then we'll do it with the box plot. So let's copy this again. New page. Oh, the copy doesn't work. Fine. Screenshot it. Come on, behave. There we go. All right, so let's see, what was our mean? Our mean is about 66.5, and the standard deviation is about 4.3. Let's just go to 1 decimal point because it's easier to graph. So we've got our mean. Mean, there we go, which is X bar is about 66.5, and our standard deviation, often abbreviated with an S, is about 4.3. So on the graph, I want to mark my 66.5, so that's going to be about here is my best guess. So that's my mean X bar. Standard deviation, again, is the average distance from the mean of all the data values. So from the mean, we want to add and subtract the standard deviation. So we're going to have the mean in the middle, and then we want to know from the mean, what happens if we add a standard deviation? From the mean, what happens when we subtract standard deviation? So 66.5 plus 4.3 is 70.8. Would be 1 standard deviation above the mean. So that's going to be around here-ish. So I'm just going to call that 1 for now. And then if I subtract a standard deviation, that's going to be 62.2. So 62.5 is here, 62.2 is around there. I'm going to call that -1 because I'm subtracting 1 standard deviations. And the X bar, we could also call that 0 because I haven't moved from that center. We could also take that mean and add 2 standard deviations. So if I add 4.3 to this, that's going to give me 75.1, I think. Which is pretty close to right here. So that would be 2 standard deviations to the right. We could also subtract another standard deviation. So from that, to borrow for this. Oh, what did I do? I have no idea. Something happened. Subtracting 4.3. We have to borrow again. So I'm going to get a 9 there and a 7 there. And that's not 5. Excuse me, 57.9. So 57.9 is probably about there. So that would be -2 standard deviations. So the distance between each of these from here to here, here to here, here to here, here to here, should always be 4.3. So I'm close, not too bad. Now we could keep going. We could add a third standard deviation and a fourth standard deviation. What's going to happen is that within 2 standard deviations will be most of the data. So usually most of the data is within 2 standard deviations of the mean. Right, so starting at the mean, count 2 standard deviations to the right, count 2 standard deviations to the left. What do I mean by most? 95% comes up a lot, somewhere around that. So if we use that as a measure for where we're usually expecting to find measurements, then outside of that is unusually large or unusually small. So any number on this side over here, so that's the cutoff for unusually large values, and this would be the cutoff for unusually small. Numbers that are unusually large and unusually small are considered outliers compared to the rest of the data. And here we're using what's called the 2 standard deviation rule. Sometimes this is also called the 95% rule. I think 2 standard deviation rule is a better name for it because it's definitely 2 standard deviations as the measure. Sometimes it's 95% of the data, sometimes it's 90%, sometimes it's more like 98% of the data is in there. Just kind of depends on the data set. So you'll see it go by 2 different names. So let's identify in our data set what numbers those are. So we have, let's see, about 57.9 is our low cutoff. So sometimes that's called the lower fence. Lower fence for us is about 57.9. Anything below that by the 2 STD rule is unusually low. And then our upper fence is about 75.1. So anybody with a height above 75.1 is unusually high compared to the rest of the people in this particular population. If I look at my data set here, I've got my numbers, 57.9. So these numbers would be considered small by that measure. Highlight them. And then above 75.1, these would be considered unusually high compared to the rest of them. So they're outliers. So that's one method of determining outliers. Next method uses the box plot to determine what's unusually high and what's unusually low. So let's just play with the box plot for the next part. Let's see, can I just go back to the drawing? Screenshot that. Okay. So this is called the IRQ rule for outliers. And IRQ stands for interquartile range. The interquartile range is from Q1 to Q3. So my Q1 was, let's see, 63.6 and then 70. So my interquartile range, IQR, is 70 minus 63.6, which is 6.4. Let's double check on the calculator. So I'm going to add down here IQR, and that's just the third quartile minus the first quartile, 6.4. So then what we do is we multiply that number by 1.5. So 1.5 times the IQR, that's not an R, again, is going to be, let's see, 3.2 onto that. It's going to be 9.6, I think. Calculator. 0.5 times that IQR. $9.6. Got it. Once we find the IQR to identify the low cutoff and the high cutoff, the low is going to be Q1 minus 1.5 that IQR. And the high cutoff is going to be Q3 plus 1.5 times the IQR. So we're looking at the width of this box. We extend the width a little bit and then add it to Q1 to go outside of that. So what do we get in this case? For example, the lower one would be 63.6 minus that 9.6. The upper is going to be 70 plus that 9.6 I calculated. Low equals Q1 minus that 1.5 multiple of the IQR. So that says 54 is the cutoff for people that are unusually short compared to everyone else. And the high cutoff would be Q3 plus that 1.5 multiple of the width of the box. So 54, 79.6. Let's see, we had a low of 52. So this was 52 over here on the low. 54 is about here. So anything to the left of that star would be unusually low. We had a high of 78 right here. 79.6 is out here. So according to the IQR rule, I have some data values over here that are unusually low, but I have nothing that's unusually high because that high mark is above my max. So according to this rule, there are people in this survey who are unusually short compared to the majority of the group, but there's no one by this method that's unusually tall. So the two standard deviation rule, which we went over earlier here, doesn't necessarily match the IQR rule. They're just two different ways to explore, are there any numbers that seem far from the majority of data? So let's see, 54, turns out we only have one number that is unusually low by this measure. So in this case, the only outlier by this method is the minimum of 52 inches.